we are jumping straight into a paper that really makes you rethink things. Seeing without pixels, perception from camera trajectories.
It really does. I mean, the whole premise is, can you figure out what's happening in a video just from the camera's movement?
Right, with no pixels at all, just the 3D path it takes.
And the answer, amazingly, is yes. Their model, Camformer, is the key here.
Which is a super lightweight transformer that learns to connect these camera paths, these trajectories, with natural language.
Exactly. It uses contrastive learning to build this shared space where a certain kind of movement means a certain thing.
And the core insight is that the trajectory is packed with meaning.
It is. From a first-person view, how you move shows what you're doing.
And from a third-person view.
It shows what you're paying attention to, what you're observing.
And it's not just a neat trick. It's robust and incredibly efficient. It works across different ways of getting that pose data, from high-end slam to just a regular video.
And the performance gains are real. We're talking up to a 13% boost on some metrics. It often beats the big visual models on tasks with a lot of action.
Okay, let's unpack that, because the idea itself feels, well, it feels almost philosophical at first. It's based on James J. Gibson's work, right?
That's the foundation, active perception.
Yeah.
The idea that we don't just sit there and absorb images, we move to see.
We're active participants.
Right. And when you record a video, you're not just a passive lens. You're imprinting your own intention onto that recording through movement.
So that motion becomes a kind of signature.
A semantic signature, exactly.
So give us a concrete example. How does a 3D curve translate into, say, playing basketball?
Okay, so imagine you're wearing the camera. A really quick upward tilt followed by a slight correction.
The jump.
That's the signature of a layup. It's distinct from, say, the rhythmic side-to-side oscillation you'd get from just walking.
Or moving a heavy object.
That might look like a smooth downward sweep, like you're rolling a tire. The curve itself tells the story of the action.
But in computer vision, trajectories have always been about geometry, right? Things like 3D reconstruction, SLAM.
Exactly. It was always about answering, where am I?
Not what am I doing?
Right. The leap to semantics to why did I move was blocked for a long time. The main barrier was just data.
You just didn't have enough high-quality trajectory data.
Not at scale and not with good labels. You need huge amounts of clean, high-fidelity data to train these models. If your estimated path is noisy, you can't extract any meaning from it. It's just garbage in, garbage out.
But that's changed recently.
Massively. We now have hardware like the Meta Area glasses giving us beautiful slam poses, and at the same time we have really good video-only pose estimators.
So the data gap is finally closed.
It's been bridged. We finally have both the quality and the quantity of data to unlock this semantic potential.
Okay, so you have this data. How do you feed it into Camformer? What's the input actually look like?
The input is a sequence of poses, and each pose is represented by a 9D vector.
All right, let's break that down. A 9D vector. 3 dimensions are for translation, I assume?
Right, your X, Y, Z position.
Yeah.
The other 6 are for rotation.
And that's a key choice, because most people would think of quaternions, which are 4D, for rotation. Why 6?
It's a really important detail they found in their testing. Quaternions can have these, let's call them continuity problems. They can jump around in ways that make it hard for a neural network to learn smoothly.
So the 6D representation is just more stable for the learning process.
Exactly. It's continuously differentiable, avoids issues like gimbal lock, and just lets the transformer learn the subtle changes in motion much more effectively.
And the pose itself isn't absolute. It's relative to the midpoint of the clip. Why is that so important?
Because you want the model to learn the pattern of the motion, not where in the world it happened. If you used absolute coordinates, it would have to learn that opening a door looks different in every single room.
But by making it relative.
It learns the general shape of the action, the twist, the pull, which is the same everywhere. It's key for generalization.
Makes sense. And for the really high-end data, they can also add in the gravity vector.
Yeah, which helps a lot. If the model knows which way is down, it really helps stabilize its understanding of things like tilting or climbing.
So we have this 9D input. How is it trained? They use something called multimodal contrastive learning.
Right. The simple way to think about it is that you're training the model to play a matching game.
You give it a trajectory, and it's matching text description.
That's your positive pair. You tell the model, these two things go together, pull their representations close.
I think you show it a bunch of mismatched pairs.
Exactly, the negative pairs. And you say, these do not go together, push their representations far apart. The influency loss is just the math that makes that happen.
And the text side of this is handled by a pre-trained CLIP encoder that's frozen, right?
Which is a brilliant move. You're not trying to learn language from scratch. You're using CLIP's incredibly rich pre-existing map of language as your target. Camformer's only job is to learn how to map its 9D trajectory data onto that powerful semantic map.
But there's a problem here. A short bit of trajectory is ambiguous. A little hand movement could be anything.
That's the core challenge. So they came up with this idea of contextualized trajectory encoding.
Meaning you look at a bigger chunk of time.
Exactly. You feed the model a wider window, maybe up to 8 seconds of context around the main action. This context, the before and after, helps the model disambiguate what's happening in the middle.
But doesn't that risk diluting the signal? If I care about chopping an onion, I don't want walking to the counter to mess up my final result.
And that's the clever part. The transformer sees the whole context, but for the final output, the final embedding, it only pulls the features from the original local action window.
I see. So the context informs the representation, but it doesn't pollute it.
Precisely. You get the best of both worlds. Global context for disambiguation, but a sharp focus on the local action.
Let's get into the results, starting with the egocentric, the first-person view. They found a really clear split in performance.
A very clear dichotomy for what they call physical activities, things with big, clear body movements like basketball or bouldering Camformer, was incredible. We're talking over 90% accuracy.
But for procedural activities, not so much.
Right. Things like cooking or bike repair, where the motions are much more subtle.
So why does it struggle there? Why can't it tell the difference between stirring something and turning a small screwdriver?
It comes down to semantic resolution. The physical difference in the trajectory between those two actions is tiny. It's a subtle wrist rotation. It's just too low magnitude, too easily lost in noise for a motion-only signal to reliably distinguish. Vision is still king there because it can see the spoon versus the screwdriver.
So it captures the verb rotate, but not the noun spoon.
That's a great way to put it.
But even with that limitation, the efficiency is just staggering. You look at a task like text retrieval, and Camformer is using, 0.02G MSEs?
And a big vision model like EgoVL-PV2 is using almost 90. It's a mind-boggling difference.
Over 4,000 times cheaper computationally.
And for those big physical actions, it's not just cheaper, it's better. It actually outperforms the visual models.
Which is huge for anything on an edge device.
Absolutely. And it has this unique strength in what they call out-of-view scenarios.
Situations where the camera can't see the key thing.
Yeah, the bouldering example they use is perfect. If the landing mat is out of frame, a visual model has no idea if you're going up or falling down.
But the trajectory is unmistakable.
It's a clear, rapid downward acceleration. Camformer sees the fall even when the pixels don't.
And that unique signal also helps it judge skill level.
For sure. An expert's motion is fluid and efficient. A novice's is jerky and hesitant. That pattern is written all over the trajectory.
So it was better than the visual baseline at telling experts from non-experts.
By over 5% on average. For things like dance or climbing, that's a significant gain. It's picking up on the quality of the movement.
And even on those procedural tasks where it's weaker, it still adds value.
It does. When you fuse it with a strong video model, it consistently boosts performance. It proves the signal is non-redundant. It's adding information that the pixels just don't have.
One last thing on this.
Yeah.
Robustness. This was all trained on high-end SLAM data. How did it do with messier estimated poses from just a video?
Incredibly well. The model pre-trained on the good data was always better than a model trained from scratch on the noisy data. It shows that learning the fundamental patterns on clean data is the way to go.
And in the process, they sort of created a new way to benchmark these pose estimators.
They did. It's not just about geometric accuracy anymore. They found that the pose estimator Pi3 was the best, not because it was the most geometrically perfect, but because its output poses had the most semantic utility. It's a new way of thinking. How useful is your pose for understanding, not just for rebuilding a scene?
Okay, let's switch gears to the exocentric domain. So third-person video. Here, the trajectory isn't about your own body's motion.
No, here it's about your attention. It's the recorder's attentional imprint on the world.
So if you're filming a soccer game, you're panning quickly, tracking the ball.
Versus filming a statue in a museum where the camera is slow and stable, those are completely different signatures of observation.
And the results back this up. It performed way better than random chance. But the really interesting comparison was against the big multimodal models, the LMMs.
Yeah, this was fascinating. They tested it against models that first try to describe the camera motion in text and then use that text. Camformer, which just interprets the trajectory directly, blew them away.
46% accuracy versus about 33 for the LMM.
It's a really strong sign that these big language models aren't very good, yet at translating this kind of raw motion data into useful text, it's better to just learn from the signal directly.
And they push this idea further with scene attribute classification.
Right, trying to see what it could and couldn't infer about a scene, and it created a really clear spectrum.
So for static things, it's useless.
Completely. Trying to guess day or night from camera motion is a random guess. There's no signal there.
But for dynamic attributes,
It's highly predictive. It could classify people walking with over 80% accuracy just from the way the camera operator was moving to track them.
and again, this generalized well. It showed gains on other benchmarks like FineGym and UCF Dynamic.
Yep. The pre-trained model consistently provided a boost, proving the knowledge transfers.
Let's go back to the idea of context for a second. They figured out there's an optimal amount of context to use, and it depends on the task.
It does. For a global label task, like classifying the overall activity in a whole clip, more context is always better.
Because more of the clip gives you more evidence for what the overall theme is.
Exactly. Performance just keeps going up with sequence length. But for localized label tasks, it's different.
Like finding one specific key step.
Right. For those, there's a sweet spot. Performance goes up, peaks, and then actually starts to decline if you add too much context.
Because the irrelevant motion before and after just becomes noise.
It pollutes the signal you need for that very precise local prediction.
You know, one of the coolest emergent results for me was the repetitive action counting.
Oh, yeah, that was fantastic.
The idea that it can capture the rhythm of an action.
This is maybe the clearest proof of what trajectory brings to the table. If you look at the self-similarity map of the features for an action like chopping, you see these beautiful, clear, periodic diagonal lines.
It's literally seeing the rhythm.
It is. And the key thing is, when they looked at the features from a powerful visual model like Dino V3 for the same clip, those lines weren't there.
So the visual model sees the objects, but the motion model sees the rhythm.
It's capturing a completely different and very powerful dimension of the data.
So as we start to wrap up, what are the big limitations here? Where does this go next?
The most obvious next step is a unified model. Right now, they have separate encoders for egocentric and exocentric. You'd want one model that can handle both, maybe with a little token that tells it which domain it's in.
And that fundamental resolution limit is still there.
It is. It can tell you how something is being manipulated, but not what is being manipulated. It will never be able to tell stirring tea from stirring paint on its own.
And the whole pipeline still depends on getting a good pose estimate to begin with.
That's the bottleneck. If your pose estimator gets confused by a big moving object and thinks the camera moved, the whole semantic interpretation falls apart. We need better, more semantically aware pose estimators.
So, to sum it up, this paper really does shift the paradigm. The camera trajectory is no longer just a tool for geometry. It's a real semantic signal.
It absolutely is. And it leaves us with a really provocative thought. We spend so much compute, so much energy running these massive, dense video models. Given how cheap and effective Camformer is, how could we redesign our systems? Could you build, say, a real-time sensing pipeline for a low-power device that is motion only, in places where you can't use pixels for privacy reasons or just can't afford the compute? What meaning can you extract when you are intentionally blind? It's a radical question.